video, we are going to implement a self-organizing map on breast cancer dataset using TensorFlow library. So follow us in this video. First, we need to import the required libraries. Here, in this part of the code, you can see that we have imported the CSV, NumPy, TensorFlow, and Matplotlib libraries. We have loaded the breast cancer dataset from the CSV file that we have downloaded from the UCI archive website. The dataset is given to you in the form of a CSV file. Here, in this part of the code, you can see that we have read the CSV file and saved each row in the list. Then the list is converted into a NumPy array and the number of the samples and the features are extracted. This dataset has 569 samples of benign and malignant breast cancer and 30 diagnostic features. The first row of the dataset has the title of the features, and the first two columns have the ID of the patient and the benign and malignant flags as B and M respectively. So in this part of the code, you can see that we have changed the M or malignant flag into 1 and the benign or B flag into 0 and saved the result as labels. The first row and the first two columns are deleted from the dataset, and the rest, which is real data, is stored in the data NumPy array. Here, in this part of the code, the parameters of the model are defined. The number of the iterations is set to 100. Initial learning rate is 0.01. The output map has the dimensions 100 times 100. The total number of the weights would be equal to the multiplication of XY axis of the output map and the number of the features that we have, which is 30 here in this example. The network dimension is the initial size of the neighborhood around the winner, and the sigma null is the initial neighborhood radius. Time constant t that we see in the formulas is related to the number of the iterations in the sigma null. So here you can see the network dimension, the sigma null, and the time constant that we were talking about. In this part of the code, you can see that we have normalized the data column-wise. We have also initialized the weights randomly and defined a session for the future TensorFlow evaluations here. As you can see, we have defined a function called BMU, or best matching unit, here. So this code, the BMU function, should give us the best matching unit or the winner. The inputs are the features of each training sample and all of the weights in the output map, and the output is the index of the winner and also its distance from the sample. So we have converted the NumPy values of the X and the weights to the tensors and changed the type to float, and since we want to use the broadcasting feature, we have used the expand dims function that you can see here in these two parts, expand dims functions, which is a function that we have already explained in most of the previous videos in this tutorial. This function, the expand dims function, enables us to get the difference of one vector, which is x here, with a bunch of other vectors of the same size, stacked as a matrix like W, and it will save time and coding space. Then after that, we have computed the distance of each weight to X by computing the subtraction and summing over all features in one vector, and then taking the square root and evaluating the L2 norm or the distance by running the session for the tensors, as you can see here. Then the summation is done here, and the square root is taken here. So after we run the session, we can make sure that the tensor will finally have the values and they are finally evaluated. In this line, we have used the argmin function in order to find the index of the closest unit with the smallest distance, which is the winner. And as you can see, the outputs are the index of the winner and the distance that the winner has from the input. In this part, we have implemented a function called findIndex in order to find the 2D index of a vectorized matrix. We get the number of the columns and the vector index as the inputs, and the output gives us the row and the column of the 2D representation. If you write it down on the paper and try out to find the rows and the columns, you can easily figure out the two relationships that we have written here and there to find the rows and the columns. It's pretty simple. If you just write it down on the paper, you would be able to figure out why we have written these two lines. So these three functions are the implementations of the decay of the neighborhood, the learning rate, and the influence of the winner on the neighbors, and they follow the formulas that are mentioned in the slide before. If you just take a look at the slides that we already talked about, you would be able to find these formulas. Here in this part of the code, which is actually the main part of the code, we have implemented the SOM or self-organizing maps. For each iteration, we get a training sample which will have 30 features, and we call it S, as you can see here. Then we call the BMU function in order to find a winner among all weights, as you can see here. By calling the findIndex function, we find the index of the winner, and in the next steps, we have decreased the neighborhood size sigma and the learning rate eta by using the functions that we already defined above in the above lines. Then it's time to update the weights according to the winner that we already have found. So in the nested for loops, we find the neighboring units of the winner such that they are in the radius r of the winner. Then we find the influence of the winner on its neighbors and update the weights according to the formula that we already have, which is also mentioned in the slides. This process will be repeated for a specific number of the iterations that we have already defined in this code. So the nested loops that I was talking about is shown here. After the iterations are done, we get the weights vector that has all of the weights related to the inputs, and the inputs have trained the weights as a model so that it can be a 2D representation of the data. Here, in this for loop, we have found the 2D representation for the weight vector, and after finding the mean of each weight vector, we have plotted the output map with the mean values. Since this process takes a long time, we have stopped the process after a few iterations. If you run the code completely, you can see two classes of data for the benign and malignant cancers in the plot completely distinguished. As you can see, we have plotted the results here. So great, we're done with the implementation of the SOM or self-organizing maps. It must be noted that we could also use the inbuilt functions and methods which were only a couple of lines of coding, but we prefer to walk you through the real coding of the SOM.